Welcome to this new video where I'm going to talk about very important concepts related to process design. So in this video I will cover reliability, maintainability and availability of equipment. So I'll go over some of the basic definitions first, then I can give you some formulas that you can use to calculate these values, and then finally there's a sample question to test your knowledge on this topic. Let's start off with some basic definitions. So here you can see like this diagram tells you the uptime. So this is where your equipment or whatever you're looking at or your process is working versus the downtime. So the downtime, this is where whatever you're looking at is not available. So then the reliability is defined as how long a system can survive. So that goes from the entirely uptime until you actually have your downtime and it needs to be maintained. So the maintainability is associated to how long the system's downtime is, where you probably are repairing the equipment until it goes back to the up state. And then availability associated to the percentage of uptime that you can get over a specific period of time. Now availability is important for a number of reasons, mainly because it's directly related to profit. So once your process is down, it means that you're not producing whatever you want to produce. So you're wasting resources. So that's why it's a very important concept. But reliability is also important from a safety perspective. So think about if you have specific pieces of kit, so think of pumps or vents. If they are not working, that can also be a safety hazard. So that's the other aspect that we need to consider here. So the first thing we're going to have a look at is the failure rate. So the failure rate always looks at specified conditions and for a specific period of time. So here we can see two concepts. So we look at the fraction of the number of components that failed at a specific time. So you can see we start at 0, because obviously when you start off everything is actually working. And then you can see slowly over time everything will lead to failure, the maximum value where it plateaus is at 1. Now the reliability works the other way around. So it's the fraction of the components that survived at time t, and they're the mirror image of each other. So as the fraction of failed components is going up, your reliability is going down, so you can map them onto each other. Now, so what's important here is here we look at an indefinite period of time, and we look at things that are put under the same design, and we look at very specific conditions. So would you change those conditions, the curves would also change. Now, what you then often get is when you start considering this, and what you inherently see in a lot of processes, is that you have standby equipment, and this is particularly important for pumps. You can imagine if something is not pumping, you get like a build-up and you get a blockage, which is very dangerous in addition to losing profit. Or you can have parallel trains. So it means that if you have maintenance in a specific system, you can switch to a parallel train and you can make sure that you don't have downtime. So this is also when you start to kind of predict when this failure is going to happen, and you prevent that by having regular maintenance. So the first thing that you then need to have a look at is how you can actually calculate these values and the failure rate. So now we've looked at the general concepts. Now let's look at the formulas that are important here and how we get to the failure rate. Now, first, let's have a think about what reliability is. So it's a probability that the component or whatever you're looking at will perform the required function for a given period of time when used under specific conditions. Now, in order to get to that stage, we first need to have a look at the probability density function. So the probability density function is the probability that a component or a system will fail in a specific time interval. So we know that the capital F related to the fractions of components that weren't working. And here we're looking at a specified time. So we're going to look at the derivative of it. So now if we look at the failure rate, that means the probability that a component or a system will experience a failure per unit of time, given that it has survived so far till time t. So what we then get is the probability of failure in a time interval divided over the reliability at time t. So we know the first one, the probability of a failure in a time interval, that relates to the probability density function, so the small f. And that goes to 1 over the reliability over time, which is r. So we know that the probability density function is equal to dr over dt. And then we have to multiply this by 1 over the reliability at time t, which is 1 over r at a specified time interval. Now we know that we can solve this equation. We can see that the reliability is directly linked to the exponential minus lambda dt. So what we get here is showing that reliability is dependent on the time, which we know because the longer it takes, the more likely equipment is to fail, and also dependent on the failure rate. So specifically here we look at systems that can be repaired. So bear in mind this is not always the case. So this is a very specific example. And what you get, the time between consecutive failures includes both the failures and the repair characteristics. So sometimes knowing the failure rate is not necessarily the most meaningful. So what can be better is to measure the time to failure and to separate out the time to repair. The mean time to failure is then the uptime divided over the number of system failures. So that's kind of what you see here depicted in this diagram. Now, this is also if we presume that lambda, so the failure rate, is constant, which we will presume in this case, but just be aware that there are other distributions, particularly the Weyl distribution, which do take into account that lambda is not always constant. You can say that this mean time to failure, so MTTF, is equal to 1 over lambda. So bearing in mind, we're always looking at probabilities here. So it's the likelihood that the system will fail, but we never actually know the actual time. And in fact, if we look at when failures occur, it usually is in the shape of a BAF curve. So what we seem to have when in a system, you can imagine you have relatively more failure in the beginning, which is related to infant failure. This infant failure might be related to some hiccups in the system. Then we will see the failure will remain relatively constant until we start to get more failure because of wear off of the equipment. Well, does that mean that we are going to avoid wear off? Not necessarily. There are types of equipment, particularly if we look at mechanical equipment, that we know that this wear off is happening relatively more quickly than you would like. But all you do is when you design your process, you do take this into account. So it means you need to have some mechanism in place, whether that's maintenance, whether that's, for instance, if you're looking at sensors, that you have an additional sensor somewhere in the process that can kind of mitigate this wear off. So always a likelihood that you're going to get out of this. And I think the next slide will nicely show this, and never like a mean value. So and basically what it means, if you look at this reliability from a safety perspective, you always need to be prepared for the worst case scenario. And this is what this shows. There's absolutely no guarantee that a unit with a constant failure rate, even if it's constant, will survive to the mean time to failure. So knowing that this is 1 over lambda, we can substitute this in the reliability function, which we know now is equal to the exponential minus lambda t. Now, if you look at this table, here we can look at the probability that units will still be working. So very low on, you will see that there's almost a 90 to 100% guarantee that your equipment is working. But if we look up, because of the exponential, if we look at 1 times MTTF, here you can see the probability is already only 37%. So obviously this is in line with the equation, but in the top of your head, you would expect the majority of the equipment to survive to this mean time to failure. And because of this exponential function, this is actually not the case. So you need to take this into account when you're designing your system. The other thing you need to take into account is that the time to the next failure, let's say if you are repairing a system, and even if you're presuming that you can perfectly repair it and get it back to its original state, which is not always possible, the time to the next failure is not always the same. So this can also vary quite a lot, and over time you can imagine that the more equipment is repaired, this might go down as well. So now you would have some of the tools where you can work out more or less how long it will take roughly for your system to fail, and also that gives you an idea of what kind of measures you need to implement. So do you need to schedule regular maintenance? Do you need to make sure that you have a backup in place, etc., etc. So if you want to test your knowledge, here I have a little example where you can look at. It's a very simple example. You have a specific instrument with a constant failure rate. So this constant failure rate doesn't need to be specified, of a certain number of failures per operating hour. Now, this means you can calculate the mean time to failure, and I can briefly provide the answers here so you can have a look at it. you can work out the reliability function based on the equation that I just solved before. Then when you have the reliability function, you can work out what happens to calculate the reliability after a 30-day continuous operating period. So just have a think about this for a minute. I will provide the answers to this briefly so you can have a look for yourself in the next slide. And hopefully that shows that you actually understand the topic. So in summary, have a look back at the questions that I just showed to you. So you should be able to work out the mean time to failure, providing the failure rate is constant. So here you can see the answer that you should be getting. You can derive equations for the reliability function. Again here, taking under the assumption that the failure rate is constant. And then if you know the specific time period that you're working with, you can presume or you can calculate the reliability or the probability that your equipment is still working at a specific time period. Okay, so as mentioned, this is always a probability, so you're never going to be 100% sure. So we'll see when you do the design, you need to work on this probability and make sure that you implement appropriate measures. So in this video, I've briefly discussed some important concepts around reliability, maintainability, and availability with regards to process design. And hopefully what you'll see if you see these next videos, you can start using these concepts in order to put together an appropriate design for a process that you're interested in. Thanks for watching.